that's a good transition. I'm going to talk about some integrators, work we've done on the GPU part. We've been collaborating with the MFEM team, with a lot of application guy. That's what we do, and I'm gonna talk a little bit more on the work that has been done with the Cascadia application with Stefan and all the team there. Going to provide a guided tour, a high-level tour of what is the job behind trying to help the application code, having to optimize specific kernels for being able to address HPC runs on these machines. So we're definitely excited to see that there's a lot of students this year, new developers. So this talk is really for you to have a feel of what's going on behind the scene, behind the job of having the task to help on the GPU side. So I've been working on the MFEM side for 8 years, joined the ACP project, and participated actively in porting this library onto the GPU. So today I'm going to use most of the elements here in bold. We're gonna start with some mesh elements, some of the finite elements basis. We're gonna talk about billionaire integrators, and of course, targeting GPU acceleration on different hardware to address the portability goal that we do have in mind clearly. So I will target the AMD chip and as well as the NVIDIA GH200. Each time it's a pleasure to work with the application guys. It's good science. It's a way to embrace new equations, which means for me new integrators. First questions usually I ask is what are the equations, which means which triggers, what are the integrators under the hood, how they will be scheduled online, and some other particularities that comes with new application. It's the context. Is it going to be for a modular library for broader audience, or on the contrary here, is it going to be specifically on GPU on HPC clusters, which we'll see triggers different code path and optimization techniques that we can have. So all the point is to navigate through different versions, algorithms of these kernels, starting from raw integrators, bringing some or using some hardware capabilities, bringing shared memories, having new ways to revisit the higher level algorithms in order to have higher flops and use more efficiently the hardware. So usually we go through, we see a lot of this figures, how MFEM is using these partially assembled high order finite element operators. We do throw, okay, we're gonna, instead of using this assembled matrix A, we're gonna just use these P, G, B, D, and the transpose, and we go through. Today, I'm gonna try to show you deeper how these operators really are used down to the code. And for this, we need few ingredients. Today, I'm not going to talk about the parallel part of it. So each kernel are going to use exclusively these G, B, D, and their transpose version of them. Again, the idea is to produce these kinds of figures on the right. where for different orders, we want to reach max peak for these kernels. An important ingredient is the Bs. These finite element bases, which can be just for evaluating some degrees of freedom down to the quadrature points, or usually just comes with different flavors. But we're using some factorization, which is a series of tensor contractions, which can be visualized pretty much like this, where you start with a 2D cube tensor, and you apply dimension by dimension x, y, and z to end up at quadrature point with a 5 cube quad point tensor there. A GPU kernel overview, the best way is definitely to start with the website. The website has extensive documentation on the legacy part of what are the integrators, what are the bilinear forms, how they can be derived, as well as all the different operators that you can use. So this is more for the legacy part. We've done the transition to the GPU with the version 4.0 of MFEM, represented by this figure in the middle, where we introduced few key elements, which is, of course, the memory management in order to be able to bring the data from the CPU to the GPU back and forth, depending on what is being ported and what you can use on the GPU, hopefully transitioning everything to the GPU at some point. There's some documentation also on the GPU part, and as well as the different integrators that are available there. Then there has been some choices in order to allow development in a easy way. That means that we have a execution model where you can develop on the CPU, you develop on your laptop, desktop. You use few ingredients of MFEM, and you're able at runtime to switch for any backends that we are supporting. And again, kernels now boils down to either the integrator we provide or a way for you to, from the equation, try to derive the operators and try to distinguish what are these operators, the B, D, DB, and Gs. One aspect with dealing with a unique application, a unique code, that it brings some it fixes some inputs. So for example, here we're not trying to build a kernel for all possible orders. We have fixed 4 and 5 orders for the degrees and freedom, and only 5 at quadrature points. So that's something that is fixed. We're only going to try to optimize one line here on the GPU. It comes with its flavor. Here it's a mixed integrator. It's going to be the gradient one, which means that we have two basis functions, a test and a trial one. And again, the idea is to develop on the CPU side, use the existing documentation, how we wrote the first integrators, how you can write your own custom integrators. It gives the different again, ingredient that you can use that are used for the full matrix integrators that are all over the subdirectory of MFEM in Teg1. So there's some code, there's a lot of code, and one of the first task is to be able to recognize these the setup and the apply phase from this integrator that comes from the legacy code. So this is something really feasible. There's a lot again of example. Please reach out. We're here to help, and this rapidly should allow you to have a first version of your integrator. It's like a naive integrator. It doesn't use any hardware under the hood, but you're on the CPU. You're able to do the work and have a first version, and just at runtime be able to switch to the GPU. Quick side note, really, in terms of development, we usually try to be agile. Again, I do really appreciate the CPU GPU duality here. We're using extensively the Google benchmarks, so that's easy to use. There's again some of the examples in test benchmarks that you can use and derives from. That's really, yeah, every day's job. You develop your algorithm, show how they respond on the CPU, and just shift with it to the GPU. It dumps CSV tables that are used directly to produce these figures. At this point, it is, of course, useful to use the compiler flags to output to get first kind of feedback. It will give you some of the occupancies, numbers of register that are used, which can already give you a pretty good feeling of how the kernel will behave. So that means experience, but yeah, seeing the number of registers a kernel typical use is directly linked to its performance. Of course, there's other tools that we're using, some profilers, some high-level profiling here, so which gives you a visual view of the different kernels. So here we recognize the RK4, the two main kernels, which are here. A few of them here that for now we don't recognize, and at the end there's few vectors and the boundary conditioned ones. So this is, yeah, depending on the vendors, Rockprof and NVIDIA Inside System Computes. So that's just tools, benchmark to see how the iteration of the algorithm behaves, feedback from the compiler, and a global view of how the kernels are scheduled. This scheduling is pretty useful because that's where you can recognize with the partial assembly decomposition of the operator, how they will be scheduled and scheduled online. So here I've given you for this, the transpose gradient. This is the first one represented here. The G's and the T's are here. This is something that MFEM does for you if you're using some of the integrators. It comes from the FE space class. It's kernels that are there that are you shouldn't. Yeah, they were given by MFEM, and this is that's just the gradient one. So this is the first step to recognize these and know that the kernels that that the kernels that you are going to work with will use. So usually there's the inputs, there's the B's, the basis functions that we read. There's the X and Y, and for the partial assembly, there's this is the D, which is the partial assembly setup data that has been pre-computed. So most of the kernels are like this. Declare the shared amount of memory you need, the buffers and the output spaces you need. There's this B's. You end up that's the tensor contractions we've seen, and you end up at quadrature point doing what the integrator is supposed to do. So here's the transpose of the gradient, and we do the transpose of the B, D here. So this is pretty symmetric. One is the transpose of the other. And here we're using shared memory inside the kernel, and kernel is just embedded in one header file. It now has most of the time this looks like this. It can be wrapped and now registered, as Veselin explained this morning. So yeah, it's self-contained. You have everything. There's few MFEM for all, C++ now ways to wrap this lambda here and allowing to specify the launch configuration of the kernels that you need. We usually map, this is the number of quadrature data in 1D. So we usually map the numbers of quadrature points here with the block of thread that are run at in flight. So yeah, we get a 13x for we're one order of magnitude better. From initial PA to shared PA, reaching the optimized PA is usually specifying the launch bounds. There's additional values that you can set to the compiler saying that, yeah, we force you to use as many blocks in flight for each CU in order for the compiler to try to optimize a little bit more, which usually brings a little extra flops. Then it's usually, this is already good. We have a shared memory kernel, behaves pretty well. Here, we need to take a step back depending on the application. Again, we're not targeting a modular kernel. We're definitely trying to optimize this last point there, which is we are going to fill the GPU with every DOFs we can, but we are also optimizing the time to solution. So there's a trade-off there. Depending on what you want, there's some choices. One big constraint at this level is the size of each vector. Each vector now, when you're at the million degrees of freedom levels, you don't really care about the size of the vectors, the size of the geometric factors that lies under the hood in the MFEM in some of the caches. Here, there's a lot of, you cannot just leave it like this. You have to flush all the caches of these functionalities. You have to reuse every single vector that, for example, in the RK4, there are some temporary vectors there. You have to chase them, being able to pass them around, reuse them, so that, you definitely have to minimize these vector size. Another important aspect is that, we have two similar kernels. One is the transpose of the other. They're using the same parallel partial assembly data. That means that this vector at quadrature points with 5 cube size is the one that is going to take most of the memory on your GPU. So it's so big that we don't want it to be streamed twice. And the idea is to be able to get rid of these G and G transpose. This is the product or the output product of the ECP and SEED project, where we definitely saw that it was convenient to work on E vectors, the vectors that are at the element levels, but really streaming and using just an indirection map to work at the local vector level is better, which turns out that at reading, it's just using this map. And at writing, we need an extra kernel to flush the output, and we can use the atomics. So now the atomics with this version of chips do really behave pretty well. You don't need to take care where is going to happen the atomic add. Just using it is straightforward. It is better, and in our case, it allows to get rid of these two kernel, which allows us to do some reordering, reshuffling of these operators. So we get rid of these DGT and we reorder, try to put the B's in front, and in order to have these DDT streaming only once the data from the partial assembly setup. So this brings us to this best, what we call the fused PA kernel. It ends up using more shared memory. We have twice work to do the B's in front of the work of the at quadrature points. Same for the transpose, but it does the work. We don't stream twice the data. Register pressure is still manageable for these. It's the gradient. It's not too big at quadrature points. Complexity here is pretty much fine. Rapidly, what is going to take the problem is the shared memory usage. We need to be able to each B here operator has some outputs, and you need to keep each output before entering this Q data. So each line here outputs one data in a block of shared memory, and the more you have inputs, the more you need to use some shared memory. Things can be optimized more in order to avoid completely the PA data at quadrature points. That's what we call the matrix free, the MF. Even though PA was matrix free here, we even don't store anything at the setup, but we will read the coordinates, the mesh coordinates, and we will do a 3D vector gradient on these coordinates, use an additional map, do these tensor contractions only in the input, do a little bit more of the setup work in at quad point. And here starts we need to work with different implementation depending on how the compiler behaves and how much memory we do have in each chip. Going forward, as you saw, it brings us to a level of performance that is not that great. Some extra work can be done in order to really max out the occupancy of these kernels. So this is really low level, line by line, getting the feedback of the compiler to fit 3 waves or 3 block of threads. There's some hard limits we cannot go above, but that's really a work shuffling, reusing temp shared memory, computation spaces to be able to do this extra step. So this is really low level, but it pays off, and it really allows to reach another level of performance. Good news is that when we've done all this work, the transition to NVIDIA hardware was just seamless. It was the same exact kernel. Have to admit that the NVIDIA software stack, it's much more resilient to all the different algorithms that we had to develop for the AMD side. We even switched back to the shared memory version as it was preparing the next step for this optimization. It comes with visual aids in order to see where the register, for example, are used and what you can achieve in terms of bandwidth or arithmetic intensity and roofline directly. So that was nice. The last that I want to emphasize is the work that has been done in collaboration with NVIDIA and Jiqun Tu. This is he revisited the use of tensor cores for these contractions. So where the tensor core are a m by n by k matrix operations like the MMA or DMMA for FP64. So this 4th generation of DMMA instructions definitely helped. It is a 1.5x speed up compared to where we were at best with the fused PA here in thin line blue. So here again, I had to adjust the y-axis. It really gives a big speed of plus 10 gigadofs. It higher throughputs. It's definitely a new way to share memory with SMEM differently. So and on top of this, I was a little bit skeptical in terms of how much number of register it will use, but yeah, surprisingly, it is the version that used the less register. It used only 32 registers for this per thread, which was really yeah, surprising and good for good to discover. Yeah, it was a quick guided tour. I wanted to share this experience with you. Contribution exchange. We're here to help. You've got integrators. Yes, ping us. We'll bring that into the pipeline, and we'll find time to help you. Again, it's a pleasure to work with the applications to help them narrow the development sometimes to achieve these levels of performances. It allows us also to exchange, find new ways. There's still some work in progress. We know that the algorithm, there's not one for all. There's some for the low order ones, the other for high orders. There's also new developments such as DFEM that are pushing, that are requiring to have an arbitrary number of arguments. And we saw that each argument takes some resources each time, which is an open question and some active development now. Thank you. Header. Here it's a gradient. We're fusing a lot of stuff. These kernels starts to be big. But as you saw, it's just API calls. Quadrature function is still, I admit, a little bit low level. But again, with some of the development with DFEM, we're hoping to merge and maybe introduce new ways to generate the kernels. There's LLVM, there's IRs that are pushing. So again, we're open to discussion. It's a good time to revisit this. There's definitely new ideas, and yeah, it's a good time for kernels development and optimization. Yeah.
Are the optimized kernel codes somewhere available?
So there are definitely some in some branches for either the DFEM or some of the vector mass and diffusion that we've been working this year. So these are in the pipeline being reviewed, I think, and should be available. Yes.
What about the Cascadia specific
So
ones?
the Cascadia, I will maybe forward a question to Stefan here.
No, eventually?
Yeah, eventually.
Okay.
Once it's cleaned up and useful.
Yeah.
Eventually was the answer. Okay.